All right, good afternoon. Welcome to this session. This is ARC335, Designing for Failure, Architecting Resilient Systems on AWS. My name is Harsha Nipani. I'm a solutions architect with AWS. And with me on stage is Vinay Kola. He's a software engineer at Snap Inc. And also with me is Pawan Agnihotri. He's a senior manager with the solution architecture team, also with AWS. This is a 300-level session, so there will be some content that I'm going to skip over in the interest of time. But I'm assuming some of you already have background with AWS and AWS services. And here's the agenda topics for today. I will be covering the first two topics, the risk and resilience, and also technical considerations from AWS services perspective. And then in the next segment, customer use case, Vinay is going to walk us through how they have architected their Tier 1 services using AWS services and also patterns that they have deployed. And after that, Pawan will walk you through the continuous resilience model, how to some of the principles behind that, and some of the patterns that we have seen in the industry. And then finally, we have some takeaways in terms of other related sessions that are relevant to the topic, and also an AWS white paper that Pawan and a bunch of people have co-authored to give you more dive-deep analysis into some of the important design aspects. All right, with that, let's dive in. Risk and resilience. The financial services industry is one of the most critical and heavily regulated industry, and it requires resilient applications to serve businesses and customers around the globe. In 2003, the United States financial regulatory agencies like the Federal Reserve, the Office of Comptroller of the Currency, the OCC, and the Securities and Exchange Commission, the SEC, have come up with a set of regulations in terms of requiring specific RTO, the recovery time objective for agencies, to implement RTO of 2 hours for most critical applications. This is not specific to the FSIs. There are other industries who have similar mandates in terms of RTOs and RPOs. So looking at those regulated entities who have to subscribe to those RTOs or RPOs, one of the core tenets for good application design practice is to design for failure. And as the Amazon CTO, Werner Vogel, says, everything fails all the time. Resilient applications provide continuous service despite disruption, and the disruption can take many forms, from natural disasters to human error, or introducing bad code, or hardware failures. So if you take into account those considerations, customers in the financial services industry and other industries have sought guidance from AWS in terms of what are some of the best practices in terms of implementing Tier 0, Tier 1, which is mission-critical applications on AWS. And several factors are driving these requirements, such as the financial impact, the regulatory response, as I indicated earlier, reputational risk, user impact, data loss, and other aspects. So these requirements typically carry a bunch of KPIs, the key performance indicators. And these KPIs, at least in the industries that are tightly integrated with best practices of IT, they use RTO and RPO objectives in order to define those resiliency requirements. And as explained in the, if you're familiar with AWS well-architecture framework, the well-architected reliability pillar gives you some details in terms of service availability, which is service availability is commonly defined as the percentage of time that an application is operating normally. And these are represented in terms of the number of nines. Some of you may be familiar in terms of 4 nines of availability or 5 nines of availability. These are derived based on your business requirements, which are translated into RTO, RPO, which are then translated into the nines. So with respect to prescriptive guidance, what AWS essentially helps customers is to help you break it down what those mean in terms of services and how we design our services. We spoke about AWS well-architected framework, and there is also, as you probably know, AWS shared responsibility model. based on the application stack that you have, whether it is databases or storage or compute, based on the service that you're consuming, the shared responsibility model changes. And please pay attention to the stack that you have so that you know which ones are responsible by AWS versus your responsibility. At a high level, again, AWS manages security and availability of the cloud, and you as the customers are responsible for application security and availability in the cloud. Now, let's talk a little bit about AWS services themselves and how we deploy the control plane and data plane elements into the AZs. The first and foremost is the construct, which you probably are already aware, the regions and the availability zones and networking. Again, at a high level, AWS region is a separate geographic area where cloud resources can be instantiated by you as the customer, and availability zones are essentially a collection of one or more data centers which forms a campus within a region. And availability zones, as you probably know, are separated and independent and are built with highly redundant networking. And we employ multiple application design constructs with different levels of redundant components. And one of the ways we do that is the fault isolation zones. Fault isolation zones, so we just talked about multi-AZ architectures, right? We strongly recommend customers deploying tier 1 or highly critical production applications into multi-AZ architecture. But also what we do from the services side is not only AZ, but also we deploy in a cell-based architecture. What is cell-based architecture? Cell-based architecture is we micro-segment resources, even within an AZ, into smaller chunks of resources so that each resources are independent of each other. So when we deploy, do code push, or if there is a hardware failure and things like that, it is much more localized than just an AZ. So when we're pushing code and things like that, it's going into a cell-by-cell basis so that you are constraining that blast radius to most minimum affected resources possible. So that is one. Number two is microservices architecture. You may be familiar with that. If you have, a lot of enterprise customers also have applications that have upstream dependencies and downstream dependencies. We understand that, but the way to construct that on AWS to make sure you are set up for success is loosely coupled systems, and the best way to do that is microservices architecture. That is essentially the path forward. And in addition to that, distributed systems architecture, some of the call-outs here is throttling. As you probably know, we throttled some of the APIs to make sure our services are functional, right? You cannot just run millions of API calls against a service just to make sure our control plane is able to respond to those API calls. Similarly, you could do something like that, throttling your APIs. And also error retries. If you encounter 5xx errors, most likely if you contact AWS support, we'll let you know that you should try to incorporate in your development patterns to have a error retry with an exponential backoff. That is a standard industry best practice in terms of software design. And also introduce circuit breakers. So with that, again, now let's start with the global connectivity options. Whether you are born in the cloud or a customer using hybrid deployment, meaning on-prem servers, and also you have workloads that are in the cloud, it all starts with the global connectivity options from AWS. We own the fiber that's connecting the direct connect between different regions and the points of presence across the globe. I'm not going to go too deep into this. This is probably something already you're familiar with. But the general tendency is, OK, now that I'm architected well within the region, there may be your business requirements or regulatory requirements that will drive you towards having an out-of-band, out-of-region resiliency as well. This is typically, even in the data center world, you would have your primary data center and a DR data center. And that is essentially the way to address that is there are 4 strategies. Backup, restore, pilot light, warm standby, active-active. Not all applications go into a single strategy. It all depending upon your tiers, you would want to adopt different strategies. Again, backup restore, pretty straightforward. You're from one region to another region. You're essentially backing up all your data, your configuration, and restoring on the other side. Most common pattern for this is S3 replication and things like that. Keep in mind when you're doing this, you should be aware that RTO, RPO are high if you go with this approach. So if you have very critical applications, you don't want to be considering this as an option because it'll take more time to bring up resources in the DR region. And the second strategy is pilot light. Again, in this scenario, RTO, RPO are better than the previous example. But here, you're replicating your primary data set into a DR region. There are tons of options in terms of replication. I will be covering that in the next segment. But essentially, you are replicating the data set and also the configuration. Very, very important. If you are doing CI/CD, please make sure you have a pipeline delivering the exact same code. Whatever you're delivering to your primary region is also pushing the same code to a DR region, right? So that, why do we do that? Because to make sure there is no configuration drift and whatever the configuration parameters that you have supplied are consistent. In the event of an outage and it is breaching your SLAs in terms of RTO, RPO, you fail over to the DR region and bring it up. The third strategy is warm standby. Again, a lot of this is probably the most common use case in the enterprise segment. What I have seen is you're replicating the data set, but also have a set of services already deployed in your DR region. And in the event of an outage, essentially what you're doing is pushing an autoscaling. You're adjusting your autoscaling groups to bring up your full production stack in the DR region. Much better RTO, RPO in this scenario. And how are you flipping the traffic? It is essentially a DNS switch at the Route 53. Of course, there are multiple options in order to do that. Active-active. This is complex. I'm just giving you one pattern here. There are multiple patterns. There is a session on active-active multi-region design. If you look up, I think it is either tomorrow or Thursday. I encourage you to attend that session if you really want to go active-active because it is extremely complex. You need to understand a lot of nuances in order to pull that off. One strategy here is, so you're doing the snapshot replication to make sure, again, that your standard AMIs and all the configuration is replicated. The database is replicated. In this scenario, say I'm giving you an example where users in San Francisco are going to US West 2 region, and then users in Taipei are going to Asia Pac region, right? This pattern is called read local, meaning you are reading all the configuration and accessing the resources locally in that region. And then if you have read-write activity, so reading is still local, but in a scenario where you have to write to a database, you are essentially writing globally, meaning to one region. Why? Because if you have strong ACID requirements and data consistency is important for you, you cannot take data corruption or inconsistency. This is the model that you would approach. So read locally, but write globally. So as you can see, the users in Taipei will go right to the, and as indicated in the blue line, is writing to the global region. The problem here is obviously the users in Taipei might experience a little bit of latency writing to the database because they're traversing longer distance. So that's something that you have to take into account into your service design to make sure you record the latency and adjust accordingly. So there are, before I move on, there are other strategies that you could do data sharding. So with data sharding, what you could do is the sharded data set, shard 1 is only users in San Francisco can write to the data sharded set in one region. And data shard 2 is available in APAC, and the APAC users will write to that. So that's another one. So there are multiple strategies to actually do read locally and write locally as well. But there are, again, there are some nuances that you need to consider. Some technical considerations that I'd like to call out here. S3 replication. If you have a requirement to replicate your objects to other region, a standard way to do that is enable S3 replication at the bucket level or the prefix level or the object level. It's pretty straightforward. This is no different in terms of the replication, what you have in terms of if you have a data center and if you're doing SAN replication using SRDF, think of that as similar to SRDF replication at the object store level. The one important call out here, the replication time control. We launched this feature a couple of weeks ago for customers who have a requirement for RPO guarantee, meaning I'm doing SRDF replication on-prem between 2 data centers. I know the SLA is 15 minutes. Amazon, can you provide something like that in terms of an SLA guarantee? That's what replication time control gives you, is essentially if you have a regulatory requirements, most of the objects that are replicated is within seconds, but we have 99.99% guarantee that most of the objects will be delivered under 15 minutes. So if you have 15 minutes or less SLA for your critical application for replication, please enable RTC. There are others, EBS snapshots. Again, you probably are aware, you can do cross-region EBS snapshots if your data store is primarily on EBS volumes. DynamoDB, very important. I just mentioned to you about read locally and also write locally or write globally. This is a fully managed multi-master, multi-region database using DynamoDB global tables. That's the advantage you get in terms of you don't have to worry about the replication. You don't have to worry about whether synchronization is happening or not and things like that, because with DynamoDB global tables, you get that option. So if you can adopt your application data set into a NoSQL database, then this is the option for you to consider. If you are using relational databases and using RDS, say MySQL or Postgres, and you want to do something similar, so what you could certainly do, so you don't have today multi-region, multi-master option. That is something that's in the works. But what you could certainly do is cross-region read replica and make sure you promote your read replica. In the event of the disaster where your primary region goes down, you take your read replica in the other region and promote that to be the new master and reroute all the traffic, the write traffic to that replicated region. And then, so that's essentially how you promote. And finally, VPC networking, this is also extremely important. So one way to make sure, so we talked about data, replicating of data, but also there is connectivity options, right? You have resources in region 1 and resources in region 2. One of the most common patterns is, okay, I want to have the resources talk to each other. One strategy is, okay, I want to do VPC peering. VPC peering gives you that capability using Amazon's network backbone to talk to resources across 2 regions. This is not traversing the internet, so this is all going through the private channel, so you don't have to worry about that. But if you are an enterprise customer having hundreds of accounts and potentially hundreds or 200 VPCs deployed, managing those VPC peering connections can be an operational nightmare, right? I mean, as an operations person, you need to keep track of what you're peering and things like that. So one strategy a lot of enterprise customers have adopted is, instead of doing VPC peering for every single VPC, I'm going to deploy the most common applications like IDP and like my authentication services and monitoring services into a centralized shared services VPC, and have those centralized shared services VPC peered, and the rest of the VPCs are connected locally to the shared services VPC. That way, you are still having that cross-region capability. If my shared services is down in one region, I can still go reach out my shared services in the other region without having to do a complete failover. That's the strategy behind this. And then finally, this is the most important piece, where if you are a hybrid customer, you have on-prem resources, you have resources on AWS, a typical standard format would be your data centers are represented on the right, and then you have a direct connect connection in the middle. We strongly recommend make sure have your dual DX links, right? And your port speeds can be 1 gig or 10 gig, but most likely for an enterprise customer, we would strongly recommend 10 gig connection for that bandwidth and throughput utilization. And then we introduced, last year we introduced the concept of transit gateway and DX gateway. The advantage of this is, first of all, if you are a large, again, go back to the previous example, you have hundreds of accounts, you say if you have a regulation to maintain VPN connections, Then you have to maintain the BGP connections of all those VPNs between the CGW, the customer gateway, and the VPG, which is the virtual private gateway. That becomes another operational nightmare to maintain all those VPN connections. So with this design, you can the transit gateway becomes your hub and spoke model, where hub is the transit gateway and spoke is the spoke VPCs. And if you have egress control, again, a lot of customers also tell us, we don't want any IGW or public subnets in our VPC. What do I do that, and how do I scale? One method of doing that is going through the transit hub VPC as on the top, where you control all your egress routes. And all your workload VPCs will, if they have to egress out to the internet, they egress through the transit gateway, go to the transit hub, where you can do filtering and proxy connections and things like that. To help you scale there. This will give you much tighter control in terms of east-west traffic, which is VPT to VPC, and also the north-south traffic, which is VPC to back on-prem. And if you have any connectivity options like VMware on AWS, the VMC, you can have those VMware connections also terminate onto the transit gateway potentially. And just today, we launched a new feature. From today, there is inter-region VPC peering. So I need to update this deck. So you don't have to necessarily do that shared services cross-region VPC peering. You can absolutely go with transit gateway inter-region VPC peering. With that, so having discussed all this, let's review with Vinay how Snap has implemented their Tier 1 services.
Thanks, Harsha. Hey, so my name is Vinay Kola, and I'm an engineer on the data infrastructure team at Snap. My team owns the user and friend graph infrastructure for Snapchat. And today we're going to talk about how we've architected our services on AWS, keeping operational resilience in mind. But first, in case you haven't transformed yourself into a dog using our lenses, let's talk a bit about what Snapchat is and the role we think we play in our users' lives. So our product is largely built around communicating with your real friends. These are the people that you can be authentic with, who you can really be yourself with without thinking too much. All messages and photos and videos on Snapchat are ephemeral, and we think that lends an authentic feel to the communication that you have. People tend to be more real when what they're saying isn't going to be recorded on the internet forever. And so this kind of flows into a lot of our product, including our creative tools like Bitmoji, lenses, filters, or even Snap Maps, which help you meet up with your friends in real life. Coming to our user base, we have 210 million DAU on average now, spread all over the globe, and our users share 3.5 billion, I think, snaps per day, which amounts to around 40K snaps per second, which is pretty impressive scale. One point to note is more than half of our users are outside North America, and so that means we need to build our infrastructure to have a reliable and low latency experience for users all over the globe. And so for us, regionalization is not only a mechanism to deal with failure, but it also helps us boost performance for our users across the globe. So it's a kind of like a two-pronged strategy for us. So just to reiterate, why do we bother with operational resilience? Because getting it right is pretty hard. And I think for us, we framed it in terms of our mission statement. We believe we are the fastest way to share a moment with your friends. And so once you frame it that way, it becomes clear that for us, that we need to invest in operational resilience. So this framing not only helps us decide why we should invest, but also it helps us decide where we should invest. And that leads us to availability tiers. So at Snap, we divide our services into various tiers. I think Harsha alluded to this as well. So at the lowest tier level, we have our infrastructure layer components. So these are things like our service mesh, without which almost no services at Snap would be able to operate. At tier 1, we have our services that are needed for our critical user flows, so like sending messages, sending snaps, posting stories. And so we have messaging as well as our user and friend services in that tier. And the way we incorporate these tiers into our architecture is that a given service is in any tier n can only take a dependency on a tier on a service in the same tier or in a lower tier. So for example, messaging would not be able to take a dependency on stickers. And this helps us avoid a common failure pattern where outages in relatively unimportant services have a cascading effect and lead to a much larger blast radius. So we never want, like if stickers is down, we never want that to impact messaging. And so this helps us build our architecture in such a way. So today, we're going to do a case study on the user and friend service, which my team owns at Snap. So firstly, let's just talk about what data this service is responsible for. So this owns the core user profile data. So this is your username or display name that you display yourself as on Snapchat. It's also responsible for the friend graph data. So who your friends are, can they see your stories, can I send a snap to this person or not, that sort of data. And since the messaging flows and story posting flows require access to this data, it's a tier 1 service in our architecture. Coming to the access patterns that this service deals with, today we're going to talk largely about the online access pattern, but there are other common access patterns within Snap for this service. Our data scientists perform a lot of offline analytics on the user base, as well as network-based analysis on the friend graph. And so we provide daily exports of this data to our data scientists. And additionally, we've seen a rise in near real-time use cases. So these are use cases like search indexes where they could be updated offline, but they actually have a lot of value from updating their data in closer to real time. So we've seen an increase in these kind of use cases, and we've kind of kept all of these access patterns in mind, even while developing our online access patterns and how we deal with resiliency over there. Cool. So before thinking about the future, we obviously need to learn from the past. So in the past, we had a monolithic service hosted in a single region. And as you can imagine, that came with a bunch of issues. Since it was a monolithic service, issues in any component of the app would have a large blast radius. And this goes against like the previous tier-based logic where stickers should not have an impact on messaging. Additionally, since we were hosted in a single region, we were not well isolated from performance and availability issues in that given region. So that again affected our reliability and availability. And finally, since we were in a monolith, we had other external service teams within our monolith accessing our user and friend DB directly instead of going through our APIs. And often, they would use parts of our data that we would have considered implementation details. So this made it very hard for us to evolve our data model, especially as we evolve our product over a span of like 7 years. So these were kind of the problems that we set out to fix as we built our new architecture. So to fix the data access issues that I just mentioned, we decided to transition to a service-oriented architecture. So this means all access to our data is always through an API that we have defined and we control. So this lets us hide all of the implementation details, evolve our DBs, or however we want to store our data in the background without affecting our customers, which are with our other services within Snap. So that helps us over there. The second decision that we had to make was how do we do our multi-region architecture. So Harsha alluded to this, but so for us to achieve both resilience in the case of failure as well as the performance boosts for our users across the globe, we decided to go with a multi-region active-active architecture. But there are a few variants of these. So in any multi-region active-active architecture, the reads are going to be local. So that side is pretty straightforward. But on the write path, I think there are a few different options. So we have write global, which is where all writes across the globe go to a single region. So you have a single primary region in that case. There's also the write partitioned or sharding approach that Harsha mentioned. So here, either you partition users based on their location. So, but at any point of time, wherever that user is in the globe, they would still always write to their particular assigned region. And finally, there's also the write local approach, where all regions across the globe accept writes. But in that case, you always need to have some sort of write conflict resolution to deal with concurrent writes across regions to the same row. So that adds a bit of complexity over there. In our particular case, we didn't actually have that many writes. Our service is largely read-heavy, and so we decided to simplify our architecture and go with the write global approach. But there are other services within Snap that are more write-heavy that have taken other approaches over here. So let's go even deeper into what our stack looks like. So let's first talk about what it looks like in a given region. So our service is hosted on EKS, so that's the top box in the diagram. Our data is hosted in DynamoDB, and all access to that table is fronted by a read-through cache. So this could be either Elasticache, Redis, or it could be any other custom cache hosted on EKS as well. So that's kind of what it looks like in our single primary region. Now let's talk about how it looks like in a regionalized manner. So as I mentioned, we want to be able to read our data locally. So that means we need to replicate our data to our secondary regions. So for a moment, let's pause on how we actually replicate the data and just think about how we would serve those read and write requests for our users. So in the read local strategy, that's what I mentioned, but in practice, the way we handle reads is a bit more nuanced. We have eventually consistent reads to be handled by the local region. So this would be either the primary region or second region, whichever is closest to you. But all strongly consistent reads as well as writes are forwarded to our primary region. So this helps us deal with any consistency issues that come up with the async replication to our secondary regions. So that's kind of how we deal with it. And internally, we have found that almost all services, even the privacy-sensitive ones, can deal with eventually consistent data. So this sort of setup actually works pretty well for us at Snap. So next, so I kind of glossed over how we do the data replication last time. So here I can, let's go a bit deeper into that. So we have the write request which comes to our primary region and then gets written to our primary region DynamoDB table. So after this is where the magic happens. We build on top of DynamoDB streams, and we've built a custom event stream service on top of that handles the synchronization to other regions. We additionally had the insight that instead of replicating to the DB in the secondary regions, we could just replicate it to a cache in the secondary region and kind of just skip writing it to the persistent storage in the secondary region. So that's why you'll see in the diagram that synchronization to the DB could be used as, for example, if the cache is down in the secondary region, you could fall back onto the DB, but it's optional really for this sort of architecture. The event stream service is also responsible for synchronizing, for emitting events to the near real-time use cases that I spoke about earlier. So we have, for example, our user search indexes that listen to events from the event stream service in this case. Now note that DynamoDB global tables could give you a similar replication to a DynamoDB table in a secondary region, but we don't use it for a few different reasons. So one is we don't have the flexibility to replicate to a cache only, which we wanted in our use case. We also wouldn't have the flexibility to replicate to other clouds, which is in line with our multi-cloud strategy. And finally, we won't have the ability to replicate to other for the near real-time use cases like search indexes. So for these reasons, we built our own custom solution instead of using DynamoDB global tables. So now the fun stuff, failure modes. So you can see, if you remember our primary region stack, we kind of had three components over there. We had our EKS cluster, which is our compute. We had our cache, and then we had our DynamoDB table itself. So these are the three sets of components that could face issues. And then we have various different modes of failures in increasing order of severity. So we could have a single instance of server going down, or we could have a whole AZ going down, or we could have a whole region having issues. So let's just talk about that matrix of issues. So if a single instance goes down in for example, our EKS cluster, the Kubernetes scheduler is just going to reschedule the pods on another instance, and we'll be fine. That's totally self-healing. And similarly, Elasticache and DynamoDB will handle such instant failures pretty much automatically. Taking that up a notch, if a whole AZ is going down, again, we're not going to run into significant issues. Our EKS cluster is configured such that our pods are distributed across 3 different AZs, and so any given AZ having issues is not going to affect us significantly. Our pods would just get scheduled on any of the 2 healthy AZs, and so we wouldn't really face many issues. Similarly, Elasticache cluster, in our case Redis, would also is also configured such that our nodes are across 3 different AZs, and so we would still be able to operate even if one of the AZs is having issues. Finally, DynamoDB itself is replicated across multiple AZs, and so we wouldn't run into any issues over there either. With respect to a whole region going down, that's where it gets a bit tougher for us. So in our secondary region, if either the EKS cluster or the DB is having issues, we have the option of failing over to another of our secondary regions or the primary region. However, if you did this blindly without any control, what would happen is the other healthy region would get an influx of new traffic and would potentially take the currently healthy region also down with it. And so to prevent this, we build controls so that we can gradually migrate the traffic and throttle the user traffic if required, just to make sure that the healthy region stays healthy. So the priority is on limiting the impact of any particular issue and not having that issue spread to other regions as well. We build these kind of controls into our service mesh rather than making it service specific, so that all services within Snap can leverage these mechanisms. So in this case, we would gradually migrate the traffic to another of the healthy regions. Critically, we would warm up the cache in that region because our service is heavily reliant on the cache, and so with the cold cache, another region would probably face issues and face undue pressure on the DynamoDB table. And once the user impact is mitigated, then we can slowly migrate the traffic back to the other region and bring it back to health. If the primary region itself is having issues, that makes it a bit harder for us to deal with. So in our case, we would largely throttle user traffic until we can nurse it back to health. For example, if our cache is going down, we would ensure that we have refilled the cache to some extent to prevent like a bunch of requests hitting our DB and causing further issues. If DynamoDB itself in our primary region is having issues, currently we consider that as like a catastrophic failure. But one way to mitigate that would be like we could use DynamoDB global tables to have a replica in another region, and that replica could be used to handle both reads and writes. So that would be one way to avoid this scenario. But currently, if our primary region DynamoDB is having issues, then we just consider that as a catastrophic failure. So that's like an overview of how Snap thinks about our tier 1 services and how we design in the face of failures. And so with that, I'm going to hand it over to Pawan to talk about continuous resilience.
Hey, thanks Vinay, and that's a great example of a multi-region architecture to build highly resilient applications with global users. You know, we're going to talk about continuous resilience now. Basically, I work with the financial sector companies, and the demand for having highly resilient applications is very high with the financial services industry, and they have very high, very low RTO requirements as well as very strong regulatory requirements. So within AWS, I sort of do a lot of stuff on resiliency and have worked on the white paper along with my team over here, and build some good assets for you to look at. Continuous resilience is something that we are building up as a future of building resilient platforms. So when we work with the customers, what we are seeing today is that a lot of our customers are moving not only the front-end applications or web applications or new applications, but they're moving mission critical. They're moving applications which are critical to business, right? So they're moving those critical workloads. For that, they require and they're asking us make sure that our applications are are resilient, right? So Harsha talked about the well-architected program, which helps you review your application and gives you a good coverage of the resiliency of your application. And these are not just financial services, right? industries across different verticals: healthcare, you take manufacturing, automotive, travel, finance. So they are all moving mission-critical applications to the cloud, right? So resiliency is a very, very important factor here. In the past, these companies used disaster recovery as a method to achieve resiliency, right? So basically, you would have a backup data center somewhere and say, okay, you know what? If I have a failure, I'm going to fail over everything to my disaster recovery center, right? So that was a standard, well-practiced method of resiliency. We are seeing a lot of companies adopt chaos now as a part of their application development lifecycle. So they go. It's not only like we're going to disaster recovery, but we're going to test our applications with random failures. There are tools out there. Netflix pioneered that. Amazon's doing a lot of work in that area. And that's what we have seen companies adopt a little bit of. It's not really what we want. We want people to be testing more and a lot more random testing. The word chaos sort of trips people up, and you can't run chaos in production. So that's a problem, right? So the future, what we are sort of looking at, is what we call continuous resilience, right? So we'll talk more about continuous resilience in the upcoming slides. I want to talk about, it's a big field, it's an upcoming field, but there are a couple of main ideas I'll try to get across to you guys about continuous resilience. So firstly, right, I mean, we all sort of know this, right? You can only be as strong as your weakest link. And if you have modern applications, there are many dependencies, and if there's one weak link in this whole dependency graph, then you're going to have the whole application fail. Vinay did a great talk about, like, if you tier your application, you should never take a dependency of a lower level tier for your application, right? So those are the things that you want to sort of figure out in your application. So it's not everybody who can do this, right? So you have to have dedicated teams who have the main job of finding weaknesses, or similar to what we talk about. If we look at availability from a different point of view, availability, security, and safety all are interdependent. They all behave and have similar characteristics, right? So for security, we do things like, what are threat vectors? So even for resiliency, we need to do the similar thing. We need to figure out what are the failure vectors, what are the modes of failure for our applications, right? So we need to do that. They have similar characteristics in the sense that it's hard to measure a near miss. A miss is as good as a mile. So if you have not captured the details of your application as why it failed, then it's hard to recover or hard to create a model to recover from that. An example of that is, we see this all the time in operations, right? People, see something failing, an operator sees something failing, and he'll at the last minute do a deep dive, and he'll save the application from really failing. But then he will not feed back the loop, right? He will not close the loop back to the developer. Hey, there's something that happened here. This is what we need to do to fix it. So that's a miss, and it's hard to capture that. Modern applications are very complex, right? For those of you who are developers in the room, doing microservices architectures and all of that, there's a lot of dependencies, and to model some of those dependencies is really tough, right? And if you don't do all of this in terms of your application, you're going to land up with catastrophic failures in your applications. So we look at this very similarly to what we do for security, right? They have similar mitigations. Availability has similar mitigations, safety and security have similar mitigations, right? So the answer here is layered defense in depth. What does that mean, right? You do some of this today. Instead of one server, you'll use 2 servers for your application, right? So you'll spread the load amongst multiple applications. You may have different network and data paths to provide you multi-path for your application. So you have some layers of defense over there. You want to design applications, and Harsha talked about it earlier. This is what we do at AWS as well, to restrict the blast radius, build bulkheads, right? So in the sense, we talked about cellular architecture, something similar, like, if you are having an application, maybe shard it in a way where a microservice servicing customers with A as their name, that may go down, but it'll still have B to Z active, right? So you are basically limiting your application failure scope, right? So you have a bulkhead there. and try to minimize dependencies. I mean, I've seen many complex applications have a dependency graph, which is crazy. You can't analyze that, right? So use microservices, use least privilege, right? Smaller microservices. That way you minimize the dependency between the microservices. And if things fail, right, it's okay. You design the overall application to work in a reduced capacity mode, right? So you have some functionality missing, but overall, the customer does have some good experience working with the application. Another important thing about these three is that they break each other. Like, I'll give an example, right? So an example here is a hacker hacks into a computer and shuts down your main application. So that main application means your availability of that application is gone. So you have lost availability. Now, take it further, right? Suppose that application was an application running in your self-driving car, right? That could lead to a catastrophe for the passengers in the car, right? So these are all interdependent and they break each other. So we have to build applications which are secure, resilient, and safe, right? So that's the goal here. So the first thing that, important thing about continuous resilience is, how do we measure that risk, or what is the risk of continuing, right? So what happens if your system fails? What happens when something in your system fails, right? I'll take an example. Suppose you have an application which runs on a computer, right, and suddenly a DIMM or memory chip in the computer fails, right? Well, your application could be smart and choose to stop and say, okay, you know what, I detected this failure and I'm going to save state and I'm going to exit, right? Give a notification, I'm going to keep the functionality. That may be good, that may be bad. We don't know. We'll have to figure that out. Or it could say, yes, I acknowledge that there's a failure, and maybe I will continue functionality with reduced amount of memory consumption. I will isolate that DIMM out of my memory space if it can, and it'll continue to function, right? Or do nothing and then fail horribly, right? Because then now you have traversed application code paths that have never been tested. You don't know what's going to happen. There's going to be memory corruption. You're going to have misleading values, things like that, which are not going to be helpful in your outcomes, right? So that's an important part of continuous resilience. You need to make some decisions as to what trade-offs as to what your application will do in case of failures. Like, if a permission lookup fails, should you stop or should you continue, right? So this is some of the decisions that you have to make upfront, and it might be okay, but it might not be okay. You have to figure out trade-offs, right? So, well, maybe it's okay, it's public data, so you can still, without authorization, you can still give the customer the data. But maybe no, it's private data, so you don't want to share that out, so you probably want to stop in that kind of failure, right? If you don't do things, you'll end up apologizing. There's a good a paper there out there, how to apologize for failures. So you'll end up apologizing for those. But yeah, I mean, these are some of the important things that you need to understand and look into for your application. The other part is continuous testing, right? How do you, many of you obviously have a backup data center, right? You may also be doing a couple of application failovers a year, right? But how many of you have actually done a complete data center failover? By show of hands, has anybody done it? Okay, 1, 2, 3, couple of. Okay, so a couple have done it, but majority have not done a full data center failover at once, right? This brings out a lot of complexities, right? And if you don't do these testing continuously, right, then basically it boils down to availability theater. Basically, it's, I have something good on a book, but I have not practiced it, and it's like a fairy tale. Okay, if everything was good and happy, we would be running, but in case of a disaster, we don't know what happens, and you don't want to be in that situation, right? I'll give you some examples of how companies, this was a big company, a SaaS vendor, who basically forgot to renew the domain name, right? Nowadays we have auto renewal and all of that, but you could still forget. I mean, these are things that you have to model your application to understand or keep track of, right? Another very common failure mode is the failure of our SSL certificates or our keys or our credentials, right? This is one of the most common failure modes, right? So another company had this kind of failure and was down for a long time, right? So again, apologies coming out, and excuses, right? So you don't want to be in that situation. This was very important experience for the financial services industry in the Northeast region when we had the failure of, when we had the hurricane, a lot of the data centers got flooded. So what was the learning there, right? Obviously, computers don't work underwater, so don't build your data centers in the basement. Learn from other people's mistakes, right? So before this, there was the nuclear reactor in Japan failure, right? And over there, that failure was due to the generator being on the ground level, which was impacted by the hurricane, right? So by the tsunami, right? So you have examples that you can see and then build them into your test plan or your resiliency plan, right? So hey, I saw someone else failing because of that. So you don't want to be the person tomorrow who has not looked into all these failure modes, right? So that's the importance of testing, importance of learning from others, and trying to test your application. Another important area is to be prepared for a failure, right? In terms of chaos architecture, you do a lot of testing, you do a lot of validation, but are you fully prepared for this, right? Are you fully, from an architecture perspective, you have a couple of layers in your application. So are the people who are going to respond to that specific instance, do they know what to do? When a failure occurs, you call them up and say, hey, this application has failed. And if they don't even know how to log into the console, or they don't know how to operate the application, or they don't know the dependencies, you're going to have a long time to recover, or you're not going to be able to recover the application. So that's something that you need to practice. So so you have game days, tabletop exercises. That's part of your preparedness plan, right? So if something's happened, how to react to unknown situations. You can do the testing of known situations, but always there are going to be situations which are something happens, it fails all the time. And this is something that, we talk about, there is no compression algorithm for experience, right? So more preparedness you have, the better it is for your application. So, application, you need to have tests in your application for certain failure modes. One of the most overlooked areas is the network fabric, right? We all assume it will work. It's mostly resilient, it's mostly available. But then it's those critical times when you really need it to work, when the failover is happening, a DNS entry is wrong, or a route, a firewall was missing, or the routes were not correct, the links were not up to date with the capacity that you needed to be. So you're going to have those kind of scenarios. You need to model those in your tabletop exercises. You need to model those into your test plans. And obviously, infrastructure, right? Data centers, servers, storage, all of that. So you have to have that to find the weakest link in any of these layers, right? So coming back to the defense in depth, right? So you have basically made sure that your staff is experienced. We have done game days. We have done tabletop exercises. They know how to react. You have built robust applications. You have a dependable network fabric, switch fabric, which you have tested regularly. You know the failover of that. And obviously, you have a good, resilient service foundation, right? So that's one of the defense in depth methodologies for preparedness. So moving into the next important category or area of continuous resiliency is observability. And by the way, I have a lot of material over here, and it's going to, sound that I'm talking too fast. But all of this will be available to you after this, and these slides will also be available, right? So you can go through them, some of these. Coming back to the observability part, right? How do you make sure you are measuring the right things in your application? A truly observable application is the one where you can measure the application functionality by just looking at the inputs and outputs, right? So if you have certain inputs, you know what the outputs are, and if without the inputs changing, the output changes, something has happened in your application. So we at Amazon do this a lot, right? So we are dealing with web services, we're dealing with APIs. So we measure things like, API rates, and we're looking at API rates. If for no reason and no input change, the API rates fell down, then we know there's some problem somewhere, right? So that's an observable system. So you want to build observability into your application. You want to be able to measure the right places, the right metrics, right, in your application. So to do this, A lot of studies have been done around systems engineering to make a safer environment from many academic institutions. This is for systems which are very critical to humanity, right? For running the airline systems, for running the nuclear power plants. So we want to take some of those learnings and move it into our application development lifecycle planning, right? So if you take from the book, this is an example of how they look at a control system, right? So you have basically a process which has inputs and outputs, and there's something happening there. Along with that, you have a controller which is looking at that application, and then you have some human monitoring the application and stuff like that. So you have a design model to go. Now, if you take this as a design model and say, okay, let me look at the hazards that this can have, right? First of all, let's overlay an application with this model. So you have a financial service application, you have customer requests for data for maybe money transfer between each account, and you have the completed actions, and it goes through this whole model. So looking at the hazards, what could happen, right? There could be a human control action issue, right? Over here, the human may be making a wrong decision. He may have taken an unsafe action to rectify something, or he may not be looking at the console properly, or he may be looking at a different console. Data is coming out in the wrong sequence. So the idea here is not to look at the blocks which are built in the robust way, but the lines connecting the blocks, right? So some output is causing, or some output missing is caused by some failure of some action, right? So that's something that we want to look at from a human perspective. There could be also, hey, your sensors are wrong, right? You are getting wrong data, or you're getting zero data, or you're getting data too fast or too slow. So there's an example, and so someone in the audience pointed out. I didn't want to bring it up, but it's a Boeing story, right? Over there, they had one sensor, and the sensor was not giving the right data. And the control system said, okay, you know what? There were two sensors, and it was not giving the right data, and basically it was forcing the plane down. So that could be one of the issues, right? So you have out of order, update too rapid, things like that. So you want to look at those controls as well, right? There may be some model issues. The perception that you have from how this application should run versus how the application is actually running. In the same example of the Boeing plane, the pilots were not trained on the new system, so they did not know how to react to the things changing, right? So they had a different perception of how to fix this problem coming in. So again, that's another area that you want to look at. So moving on to the final part of this is the risk calculation, right? So I talked about how do you make a decision. The decision is going to be based on risk, right? So we have standard risk models. You multiply the severity of the problem by the probability. That's your risk. You have a basic financial and economic model. You take that and you do some analysis, and you have that. From an engineering perspective, we want to add observability into this, right? So this is a new methodology where failure modes and effect analysis basically gives you a better view of your risk by pulling in the detectability of the problem into the risk equation, right? So you basically calculate the risk based on what you can see, right? So let's take that into an example of a layered web application, right? So you have multiple people in this application. You have people who are product managers and developers. They're looking at more of the business side, what the thing could be. You have the platform team who's looking at what technology decisions I can make. You have the infrastructure team, which is looking at how do I spread the applications. So there are going to be different failures, different probabilities of failures for each of these different layers, right? So you want to basically be able to calculate that. And I'll point out, I'm going to show some examples here. I'm going to walk through them fast. But at the bottom, we have these slides and the spreadsheets available if you want to try this out by yourself. So like for example, if we take the infrastructure, right? What are the risks that are the highest impact? Something that you don't know about, like earthquake suddenly happens and you can't compensate for that risk. For that, the ranking is the highest. Going down to the lowest is where you can mitigate, have some mitigation. So for that, you have the lowest ranking of that risk, right? So you have basically put a ranking for the severity of the effect of the failure. Take the probability of the service of the failure. I think this is a rule of thumb kind of thing. If you have history in your system, how many times things fails, mean time between failures. You can probably come up with some numbers there. But don't stress about this. Start with a guess. You have some ideas here. If it fails more than half of the time, or if it fails less than 1 in a million times, so you have some ranking to put there. Then you move into the detectability part of it, right? You cannot detect this at all. That means you have the highest risk there. But if you can detect, you have good observability into the application, then you can basically mitigate or fix that issue. So taking all the three together, you can basically here I'm going to just flip through some examples of what an application level error could look like, and you have a service lookup, DNS fails, so that's a observable error. If you have a connection to a host, no route, it's a fail fast, so you know what happened there. You have another one where you're making a request, it's undeliverable, host not found. So these are kind of errors, and you will map these, and I'll move fast on these ones because you can see them in the slide. But if you take this, you can fill up this spreadsheet and say, okay, you know what? These are my risks in the different categories and ranks in the different categories, and I come up with a risk model, and that helps me make a decision of what I should do in case my application fails, so that you can make those decisions. There are more examples here. In the interest of time, I'm just going to skip through the slides fast, so that you can at least get an idea of what could go wrong and how to view this. This is an example of an application level failure. So you have an example where the certificates were missing or security was missing, what to do, right? So you get a action out there. Again, another example here is the file. You couldn't get the file from the server. So what do? So basically, you again fill up a spreadsheet, make your risk decision, and basically focus on the high risk ones that you want to fix your application. So bottom line, you have two methods to do the application resiliency. One is top-down, STPA, which is top-down, looks at more of a business perspective, and the other one is FMEA, which is a bottoms-up approach. You get both good results in both of them, so both are useful. And I would say, finally, use some best practices when designing cloud, right? So rule of threes, make sure you have a backup of a backup, make sure you have multi-region deployment, active, things like that. Then you have fail up. So this is something that people asked us, hey, how do we design in AWS? So you probably want to be more deterministic in your failure than less deterministic. So in this scenario, if you are in US, you need to deploy in US East. Choose US East 2 as your primary region and fail over to US East 1, because that's a bigger region. You'll have capacity, you'll have lower latency and all of those things. So you can recover that way. That's just a suggestion. I mean, obviously the decision will be made based on your application. Practice. Chaos engineering is important. You have to basically make sure you practice those muscles for your applications, make sure that you know what you're doing. Give out badges of honor to application developers who have passed their application through a chaos test, because that's important. And practice continuous resiliency, right? So it's all chaos engineering, but it's a different name. So basically do like what we do for application development lifecycle. We have a DevOps. So this is like a test phase in that. Include that. Finally, I will just say about the platform. AWS is a platform where it leads to a lot of automation because it's the API-driven platform. So you can automate a lot of this stuff. Basically, build your disaster recovery processes not as manual processes, but as automated tasks and standardized automation. And finally, practice continuous resilience, and don't look for that one event or scary event of failure once a year. So with that, thank you for coming. There are certain references to the white paper, and obviously Adrian, who's very much involved in a lot of these discussions. There are some repeat sessions that are there that you can go to, and please fill out the feedback form. Thank you, and we'll be available for questions later on.